Good evening, everyone. It is my great pleasure to welcome you all to the 32nd International Materials Research Congress held here in Cancun, Mexico. My name is Teresa, and I am honored to serve as the chairman for this event. I would like to extend a warm welcome to our distinguished guests, speakers, and participants. Your presence here today is a testament of your dedication and passion for science, dissemination of knowledge, and the build-up of academic collaboration. Ladies and gentlemen, it is my honor to introduce the distinguished members of our Presidium. From the chairs of IMRC, Professor Dr. Catherine Dubourdieu, Head of the Institute Functional Oxides for Energy Efficient Information Technology, from Helmholtz Zentrum, Berlin, Germany. Dr. Felice Torrisi from the Department of Chemistry in the Imperial College London in UK. Dr. Juan Muñoz Saldaña, full professor of Materials Science and Engineering at SMMater in Querétaro, Mexico. Dr. Israel Betancourt, Director of the Materials Research Institute, National Autonomous University of Mexico. And the chair's coordinator, Dr. Mildred Quintana Ruiz, full professor of Science Faculty of Autonomous University of San Luis Potosí, Mexico. In representation of the Materials Research Society, MRS, Professor Takao Someya, professor in the Department of Electric and Electronic Engineering in the University of Tokyo, and President of Materials Research Society. As part of and in representation of our distinguished plenary speakers, Professor Yuri Gogotsi, Distinguished Professor at University of Charles and Ruth Bach, Director of A.G. Drexel Nanomaterials Institute. From the IMRC Board of Directors, Dr. Ana Cecilia Nogués Garrido, Vice President of the Mexican Materials Society. Dr. Sandra Rodil, Treasurer of the Mexican Materials Society. And finally, it's my pleasure to introduce the President of the Mexican Materials Society and Distinguished Professor of SMMater Querétaro, Dr. Jesús González Hernández. To proceed with our agenda, I would now like to invite Dr. Felice Torrisi to share a brief summary of numbers and facts of IMRC 2024.
So, thank you very much. And yeah, ladies and gentlemen, good evening. So my name is Felice Torrisi from Imperial College London and University of Catania in Italy. And I'm one of the co-chairs of this conference. It's a great pleasure for me, on behalf of all the chairs actually, to welcome you to the 32nd edition of this conference. And well, first of all, I would like to thank the president of the Mexican Material Research Society, Jesus Gonzalez, for his invaluable support and constant support throughout this journey in creating this program. And also I want to thank the immediate past president and the current president of the Material Research Society, so Takao Someya and Sabrina Sartori, for their constant, again, invaluable support, and for selecting particularly me and Catherine on this job. And I also would like to thank Mildred for her invaluable, constant, and without her presence, it wouldn't be possible actually to have such a big and very large range of symposia over here. and of course, all the technical support, and you all for making sure that this conference course is one of the largest events of material science globally at the moment. So what I want to do, I want to share a few figures with you today just to show you how this event has been growing, of course with glitches, also due to the pandemic. So if we can go to the next slide. Do we have a remote control? Ah, the remote is over there. Okay, so can you please go to the next slide? Okay, right, so as you can see this year, we have actually accepted 47 symposia. This is the largest number that IMRC has ever accepted so far, and with 44 symposia in the Congress. The total number of abstracts received is 2,588. Again, is one of the largest numbers achieved over the entire presence, the 32 years of the conference, with accepted abstracts, which actually amounts to 2,484. We have 184 symposia organizers, and the overall participation is from more than 50 countries. Again, these numbers are topping essentially all the other numbers from the previous editions. Can we please go to the next slide? One innovation that we introduced this year, these are all the symposia clusters, is actually regarding the materials for quantum technology, which we believe, all the chairs believe, is actually an emerging trend. So we really wanted to have this in this conference, and hopefully, of course, it depends on what the future chairs want to do, but we hope that this could be, for example, a growing area. And also the cluster on two-dimensional materials and materials with low dimensionality and hybrid materials, because again, this is, of course, a quite large part of the material science research nowadays. Can we go to the next slide, please? Right, and of course, then we selected, I would say, an excellent range of plenary speakers. Of course, we have Yuri Gogotsi today, which I'll have the pleasure to introduce later on. And then we have Professor Rama Vasudevan and Professor Molly Stevens and Professor Thomas Schreff. And also we have a national plenary speaker, Maria Cristina Cortinas Duran, that will speak tomorrow. If we can go to the next slide, please. So the key aspect that I want you to focus on is the last column here. So as you can see, in 2024, despite the number of plenary speakers is lower to 4, actually we have the largest number of symposia. So this clearly shows that this conference has clearly a growing trajectory and the trend is increasing. And the other very interesting number is the number of exhibitors. As you can see, there is also an industrial interest in what's happening here. So we have 43 exhibitors, and this also demonstrates the need for this community to grow even further in the future, and hopefully we'll hear more from Jesus about this. If we can go to the next slide then. And this actually reflects what I just told you, number of exhibitors. So in 2024, actually, we went beyond the ceiling of 40 exhibitors exhibiting here. And I understand from the organizer that this is definitely the largest number ever achieved of exhibitors. And actually, this was limited by the venue, I understand. So potentially, there could be even more exhibitors in the future. So overall, we could see that there is definitely a growing interest in this area. This event seems to be a right place to talk about material sciences. And yeah, with this, I'll conclude, and I'll pass it over to the next speaker. Thank you.
Thank you, Dr. Felice. Next, I am pleased to introduce Professor Takao Someya to share some work with us.
So, good evening, and thank you very much for your warm welcome. And I'm very happy to be here today representing the Material Research Society at the opening of another exciting meeting. Our society is happy to be associated with this meeting and is pleased to enjoy continued collaboration with Sociedad Mexicana de Materiales on this meeting and other activities and programs. We have said this many times before, but it continued to be true. Everyone at MRS, our leaders, members, volunteers, and staff values the excellent and warm relationship that have developed with SMMater. We hope to continue our collaborations to expand the impact of material research worldwide. Meetings like this allowed us as a community to discuss key issues that will propel the field forward, re-engage with colleagues from the world, around the world, and make new friends. In conclusion, I look forward to an engaging and inspiring meeting this week, and I offer you our best wishes for continued success. So thank you very much.
Thank you very much, Professor. Finally, I invite to the stage the President of the Mexican Materials Society, Dr. Jesus González Hernández, to officially declare the Congress open.
Can you hear me from this microphone? Yeah, right? Okay, I'm gonna go down because I wanna use my pointer. So thank you very much for coming. Welcome to the 32nd edition of the IMRC. It is my pleasure to welcome you here in this room, but also those who are connected through our virtual platforms. So, nice to see you. Well, anyway, so what I want to show you is, similar to Felicia, some slides that, illustrate the latest tendencies of the IMRC. So could we go to the next slide, please? Again, I also want to thank the chairs. Thank you very much for, putting up or achieving this wonderful technical program that, is one of the best that we have had in the last few years. They already mentioned is Catherine, Felice, Israel, Juan, and obviously wisely coordinated by Mildred Quintana. Next, please. Again, the plenary speakers, thank you very much for sharing with us your vast knowledge in many different things, many different fields that are of current interest for us, the material science and technology community. Thank you very much. And thank you for many things that you have done in the organization of this meeting. Next, please. To our sponsors, we are really grateful to them because, without the help that they gave us, this is probably not possible, to have this Congress the way we want to have it. Thanks to CONACYT, to, Army, DEFCON, to UNAM, University of Mexico, Sinvestar, Concitec, and the Air Force of the United States. Next, please. Thank you to the IMRS, for the support the whole year through. And, we really appreciate all the things that the MRS do for us. Takao, Somaya, thank you very much for that. Next. Now, similar to previous years, we have special events in the technical program of the Congress. This year is no exception. So we have programmed this nice workshop, and this is a joint workshop between Mexican Society and the European MRS. The subject of the workshop, there is going to be a 3-day workshop, is sustainable materials for energy production. The program is here, the topics are here. If you want to learn more about the program, you go to the web page of the Congress and you will find the specific topics and speakers there. Let me just mention briefly the 4 chairs. There are 2 from Europe. Juan Ramon Morante, he was the previous president of the European MRS. Thank you very much, Juan Ramon. Daniel Salazar Jaramillo, also from BC Materials, nanostructures and applications. Jaime Parada from, he is the president of a company in Nuevo León, and also Antonio del Rio Portilla, who is from the National University of Mexico. This workshop has has generated a lot of interest, as you can see in the numbers there. We're going to have more than 40 speakers, among them, some invited talks, 40 plus talks. We have 11 invited talks, we have 21 regular talks, and we have 10 short talks. And the persons that registered to attend this workshop were more than 450. So it's going to be a great workshop. We invite you to go by there. Next. Now let me show you some tendencies about the Congress, how the numbers have been in the last few years. This is an evolution of the participants. Previous to pandemic, we only have on-site participations. And as you can see, we got close to 2,000 people. Then the pandemic came, and then we start after pandemic with two modalities, the on-site and the virtual presence. And well, you see the green bars are the ones that correspond to the virtual people that was assisting the Congress, and we have a reduction in the visual presence, but we have an increase of the total participation. We don't have yet the numbers of the 2024 because we don't have them already complete, but at least we're going to reach that number, 2,000 people. So we are growing every year. Next, please. So I think that this next slide also was presented by Felice, but I want to emphasize that the Congress is growing not only in persons, but also in companies that are participating in the Congress. So you already saw that. So we started with 21, with 25, 26. Now we have over 40 companies that are exhibiting their equipments here in the Congress. So this is good news. I mean, we're growing, but there are some bad news that, the space here, the floor here at the Marriott hotels is not longer enough. It's not longer sufficient, so we have to move to a different venue. As you can see in the next slide, we are overcrowded. There is no room for anything else. There is no room for any other symposia. We have to cut the symposia that are presented in order to have, the simultaneous events through the different days of the Congress. So we took the difficult decision to move the venue of the Congress, and well, as you can see in the next couple of slides, we find a nice place. Actually, this place that I'm going to talk to you is splendid. This is a world-class facility, and this is the Cancun Conventional Center. It's obviously here in Cancun, and this is a map of Cancun area. This is the town of Cancun, and the place is called Punta Cancun. It's located right here. If we take a close-up of this area here, well, we are right here. This is a JW Marriott. This is the Cancun Center. If you want to go to the airport, you are going to take this road, this route, and then if you go to the airport from this Cancun Center, you go this way here. So it's about the same distance. That it is the same time that you are going to take from going to going and back to the Cancun airport. Now, in the next slides, there is some advantages. I think they are very important, and there is an extensive hotel and food offer there. I mean, we have hotels that which price ranges from $80 to $400 a night, so you can pick up any one that you want. We have plenty of hotels there, different qualities, different prices. So, I think that's an opportunity for us, for many people to be close together. Next, please. Well, as you probably know, we are in the process of defining our next vice president. There are two persons that have been registered. One is Juan Manuel Mora, the other one is Dr. De La Rosa. So I invite you to vote. It's already open for votation for participating in the process of designing one of the two persons that are in the process of being elected. Next, please. Well, now, take a look at this video. This is the place where we're going to be next year.
Welcome to the Mexican Caribbean, the ultimate destination for hosting successful events, where Alianza Punta Cancun awaits you. A team of professionals in the meetings, hospitality, and solutions industry, ready to elevate your event from ordinary to extraordinary. Punta Cancun is an iconic location situated in the heart of the hotel zone, where Cancun Center, the International Convention Center, is the epicenter of the most important national and international events, conferences, and conventions. With over 30 years of experience in the industry, every organizer and attendee has taken home a piece of the incredible service this venue offers. Your event will benefit from the proximity and excellent hotel offerings provided by Alianza Punta Cancun, where you'll witness the comfort and service that only recognized brands in the hospitality industry can offer. Rooms in all categories, top quality service, and breathtaking views of the Caribbean Sea. Experience your event with the utmost comfort you've ever experienced. The solutions offered by Alianza Punta Cancun are comprehensive, where every detail is monitored until excellence is achieved. Specialized DMC companies will cover all your needs at the destination. Additionally, you'll have access to cutting-edge technology in custom stand design, modules, pavilions, and signage required for your event. The experience of your event must not go unnoticed. You'll have state-of-the-art technology in audio, lighting, and audio-visual production. Your event is in the hands of an efficient, professional alliance, ready to make it a reality. If you walk alone, you'll go faster. If you walk together, you'll go further.
So this is the place where we're going to be next year. So, it's a wonderful place. It's a world-class place. So we wait there, for you, everyone here. And, I think that we're going to enjoy more. This place has more than 14,000 square meters available. It's 4 times, the room, the space, the floor that we have here. So now we are going to be more spread and, more comfortable. So, well, obviously we appreciate to the Marios, we thank to the Marios because they were very nice. They host the IMRC for more than 30 years. We are not happy to go, but we have to go because the Congress is growing and we don't want to have this limitation. The space shouldn't be a limitation for us to keep growing and growing with quality, with speakers like Yuri that, and events like the ones that we always organize. So now let's proceed to the official inauguration of the Congress. So if you should be nice and rise up for a couple of minutes only. So it is my honor, and on behalf of the Mexican Society of Materials I declare, being the 10 minutes to 7 p.m., I officially declared open the 30-second version of the International Material Research Congress. Thank you very much for coming. I hope that you stay in here, new knowledge that you are gonna get, new networking is in benefit of all of you. Thank you very much for coming, and enjoy Cancun, first of all. Thank you, and see you around. Well done.
So I think we are going to clear the podium, I guess, right? Yep. So now we're moving to, shall I go ahead? Yeah. Yeah. So we're moving to the first plenary talk. Give just a minute to clear the podium. And as I already mentioned, is our greatest pleasure to have Professor Yuri Gogotsi giving the first plenary talk here at IMRC 24. So Yuri, do you have the slide? Yeah. So Yuri is a professor at Drexel University, and he's also director of the Drexel Nanomaterial Institute. He told me to be short, but of course, I cannot really step back from saying a few words about him. So just to let you know, he received the MRS medal from the Material Research Society, I think last year, or 2 years ago. Yeah, 2 years ago. And he's a fellow of the European Academy of Sciences. And he's been recipient, he told me a few minutes ago, actually half an hour ago, of a pure gold medal, which is the Czochralski medal, said recently, right? And so he's considered, I would say, almost unanimously the father of MXenes, to the material nitrides and carbides. And I think that's what he's going to talk about today. So let's welcome Yuri Gogotsi on the stage.
Well, let me connect my computer. First of all, I would really like to thank the organizers, Felicia, Catherine, Mexican Materials Society, for inviting me. It's great to be here again. I'm truly excited about it. I will be even more excited to see my slides. And it will help me to illustrate my talk and entertain you. For the next 2 hours, I think this is the time we have before drinks will be served outside. And at that moment, I'm sure everyone will clear the room whether I finish or not. And for people who are standing in the back, there are still many, many seats in the front. Don't hesitate to come forward and make yourself comfortable. Thanks here. So what I'm going to do today, I'm going to talk about this wonderful, very large, very quickly growing family of two-dimensional materials. We call them MXenes. And give me a second to get my pointer working. Okay. Yep. You should be able to see it on all screens now. So those are 2D material built of metal atoms connected by carbon, nitrogen. They come in a variety of structures, arrangements of atoms, variety of colors, shapes, tastes, and it means properties. And what I'll do today, I will try to introduce you to this family of materials and explain why it's important. But first, I wanted to thank people who do all the work. This is my very interdisciplinary, very international group of students, postdocs, visiting scientists, who really do all research. I'm a salesperson here. I present the work they produced. And also work, of course, of many other colleagues. And I specifically featured here a student who is a Mexican, Natalia Noriega, who just graduated this year, actually from University of Brighton, acted as her co-advisor, and she did her undergraduate study and research at Drexel. But even this large, wonderful interdisciplinary group is not sufficient. I collaborate with people all over the world in many different places, many different countries, because if you want to do research at the cutting edge of science, you need a community of people. You need people with knowledge that I personally don't have, and even my large group doesn't have. And conference like this is, first of all, for all of us, opportunity to establish new contacts, find collaborators, start working on a problem we cannot solve alone. And I think this is very, very important. And of course, thank you to multiple funding sources who helped me to support research of all these excellent students and postdocs. Now, let me make a step back, a very large step back towards the Stone Age. I know this is a materials community. You all work on materials, and I don't need to sell materials research to you. But thing I wanted to stress, and this is related to role of MXene in technology I'm going to talk about, and was in the title of my talk. Materials really have been defining the progress of the society by defining the progress of technology. Stone Age, Bronze Age, Iron Age, we live in the Silicon Age now. We are moving to the time of nanomaterials, biomaterials, assembled hybrid materials here. But what is also important? Materials that determine the change in technology were not gold or diamond. You don't see them on this plot here. You see much more common materials. Those are materials that can be produced in quantities. They can be used to develop new technologies. And I will try to convince you that we are really moving to the time where we will have a drastic change in the way materials, and it means everything else is made. Because starting from Stone Age to Silicon Age, we have been taking a chunk of material, whether it's stone, bone, wood, or a silicon ingot. Jan Czochralski developed it. You just have heard about Czochralski medal from European MRS, thanks to European MRS and Professor. But we dice it, we slice it, we dice wafers, we machine out of it something. What we are able to do nowadays, we are able to take nanomaterials, two-dimensional, one-dimensional, zero-dimensional, molecules, and start assembling them into composition structures which have no analogs in nature, which are able to provide us with properties no single material can do. And that's why I believe it's revolutionary. And again, my request, people in the back, there are many seats on that side of the room. I suggest you move forward, make yourself comfortable, take a seat while talking here. Now, one more thing I wanted to mention before moving to the specific goal of my topic. Whenever we do something, we need to think whether it is going to make a difference. Difference in the world, make difference for our children, make them live in a better world, and we can leave them a better world. And people showed this US sustainable goals, other slides like this, often just to tell, oh, we do something important. But in reality, materials can really address majority of the tasks here. And I personally, when I think whether to work on a topic, I try to select topics which I know if we solve a problem, there may be a big difference. We work on energy, storage, harvesting. We work on water desalination. We work on hydrogen. And I selected not to work on some problems I know many of my colleagues work on just because I don't believe. For example, you may agree or disagree. I don't believe that by capturing carbon dioxide, we will really make a big difference. I think we just need to be much more aggressive in moving toward electrical hydrogen economy with doing these things here. And I work on topics that I believe into, that I think will be important, can make a difference, and I look critically at this, and I suggest all of you to think where we as a community, as materials researchers, can make the biggest impact. And naturally, whether we talk about energy storage, whether we're batteries, whether we're talking about solar cells, catalysts to make hydrogen or material to store hydrogen, we think nano. And nano is a big field. We have been exploring nanotechnology for a long time. I spent many years as an associate editor of a CS Nano journal, and different people put different meaning to this. For some, it's just a buzzword. But to me, nanoparticles, nanomaterials are building blocks of the future technology. And I particularly would like to stress the materials. And if you go and look how buildings are built, of bricks or concrete blocks, many materials can make different applications. But whenever you can assemble materials in a close way, like bricks in a wall or Lego stones in a structure, you can have intimate contact between particles. You can create materials which are both strong and functional at the same time. And graphene really was the first one material that attracted attention. Kostya Novoselov and Andrei Gaim, when they showed new physics in graphene, and there will be a lot of discussion on quantum properties of materials, which are related to all nanomaterials, really opened the door to designing many new materials. Some of them are very old, like a clay, moly disulfide. Some of them are new. For example, antimonine, silicene, germanium, they were not made of van der Waals bonded, weakly bonded precursors. They were created in spite of the fact of the cubic structure of, say, silicon or germanium. And in 2011, we discovered carbides and nitrides of transition metals, which I'm going to talk about today. We call it. What is also important, these materials have properties from dielectric to semiconductors to metals, but keep in mind, even graphene, being praised for its conductivity, is a zero band gap semiconductor. You need to dope it, create defects to create carriers. MXenes are actually, majority of them are true metals with a high density of state at the Fermi level, high concentration of carriers. So nowadays, we have dielectric, semiconductors, variety of band gaps, and we have true two-dimensional metals. So we can build any kind of devices. And of course, they cover a very wide range of optical properties as well here. Now, what I also would like to postulate here is that we don't look for a new miracle materials. We have been announced fullerene before, they didn't live to expectations. Next were carbon nanotubes, again, very important nanomaterials. It's all batteries nowadays. But it didn't make a revolution. And I don't think any single material can. But if we assemble these materials in the way that we get properties we need and we cannot get in any known material today, this is what is going to be revolutionary. So I think there is this change of a paradigm from wonder materials to building blocks that we, guided by machine learning, artificial intelligence, advanced computational technique, can pre-select and assemble in the way we need to attract the properties. And as you can see from our previous slide, we do have building blocks. We have already hundreds of 2D materials, and of course we can combine them with zero-dimensional, one-dimensional, and other materials. Now, after this introduction, let me switch to the direct topic of my presentation, to MXenes. So for people who are not familiar with this class of material, which we discovered at Drexel 2011, Michael Naguib, PhD student at that time, working with Michel Barzou, myself, now he's a professor at Tulane, was the first one to make titanium carbide MXene. Nowadays, we have carbides and nitrides, so X stand for carbon, nitrogen, oxygen can substitute it, of transition metals. So M stand for a transition metal. Lanthanides can also substitute for one of those metals. There come in 4 basic structures, there is more, but what is also important, the surface of transition metal will not stay non-terminated in environment. It will pick whatever is in the environment, oxygen, hydroxyl groups, but we can get also chalcogens, halogens, phosphorus, antimony, nitrogen, we predicted, or amino groups that arsenic will be there. It's a matter of time to make it here. So what it means that if you do a simple math, 4 structures, dozen of transition metals, a dozen of surface termination, plus carbon, nitrogen, you end up with at least 1,000 of possible combinations. So the first one, titanium 3C2, was published in 2011. This is a cover of Advanced Materials, and this multi-layered structure. Lamellas you see here are multi-layer lamellas. It's not single layer at that time yet here. Nowadays, we have about 50 single compositions, MXenes, about 50 solid solution, because we can match and mix transition metal on M side, or make carbon nitride, or oxycarbide, or oxynitride on X side. So really infinite number of materials if you account for all these solid solutions and mixed surface terminations here. Moreover, we're really moving to the era of atomistic design of materials, because we can make not only these simple basic structures, we can make atomic sandwiches out of plain ordered materials with, for example, one element, titanium on the surface, chromium or moly on the surface, and titanium in the middle. We can make materials with alternating atomic columns of different elements, or extract one of those and leave atomically thin trenches on the surface of the material. We can make high entropy MXenes with up to 7 different transition metals in the structure. And this is just the beginning. Don't forget about the surface chemistry. Variety of uniform or non-uniform mixed surface termination. We mark them with the letter T, terminations, and they can come in a variety of chemistries, which basically interface MXenes with the world, defining their chemical, electrochemical surface properties here. And of course, people continue developing 2D materials similar to MXenes, making borides, silicides, others. And this is a work from Linköping University, Sweden, guided by high throughput calculations. They predicted other materials. For example, they predicted the first silicide in this system and made it experimentally. So we can potentially make infinite number of building blocks. And hopefully, we will be able to really usefully use artificial intelligence to help us find the one with needed properties, and then maybe even automated synthesis to make materials we need here. And nowadays, MXenes are spreading all over the world. Research is going on all 6 continents in more than 100 countries, Mexico including. There are thousands of patents already filed. According to Web of Science, more than 70,000 people already co-authored papers. It's still very little compared to graphene. About 5,000 papers were published in 2023 on MXene. Graphene alone gets more publications. So we're still in the very beginning of the road. And you can see, first few years, there was very little interest to this family of materials. In 2016, when we showed that MXene outperformed all other materials electromagnetic interference shielding, and then they started pretty much getting into every field of applications where people have been using graphene and other 2D materials, showing the best result ever. This is where the interest started to grow and increase. Actually, data for 23 are incomplete. You also will see that actually China keeps major lead in the field, but India, Korea are quickly increasing research productivity. US contribution has been unfortunately shrinking, Europe remaining stable. I hope we can also change it, and North America and Europe can accelerate the process of researching and also using these 2D materials. And my second part of the talk will be dedicated to what we can do with MXenes. But before that, you need to understand how we make them, and then how we process them, and what their properties are, because this is how we need to select materials for applications. Determine what we can produce, what the properties are, what we need, and look for applications. So MXenes were initially made starting from a layered carbide known as a max phase. My colleague at Drexel, Michel Barzoum, is a leader in this field. The phases were discovered by Novotny and others in Austria more than half a century ago. But those are layers of carbides and nitride separated by monatomic layer of aluminum, silicon, gallium, other elements. What we did, we used electrochemical just chemical etching, selective etching techniques that I've been exploring for 30 years, initially make carbon materials, and now to decarbides nitrides to remove monatomic layers of this element like aluminum. And then we have weak van der Waals or hydrogen bonding between the layers, so we can easily intercalate, separate like other materials. We describe, really publish protocols how to make MXenes. We share our knowledge. We want people in the world to know and be able to make them. There is a couple of references. But what is important? Nowadays, we have at least a dozen of different ways to make MXenes. From initial hydrofluoric acid etching we use, to using mix of salts and hydrochloric acid, electrochemical, alkaline, gaseous halogens or halogen dissolved organic solutions, Molson salt, chemical vapor deposition. We can transform topochemically graphene, graphite, molybdisulfide, other dichalcogenides into MXene. But depending how you make them, you get different properties. When you use etching in aqueous solution, oxygen, hydroxyl groups, halogens like fluorine, chlorine get on the surface. We get materials which are hydrophilic, easily dispersible in water, but with a mix of functional groups. If we use Molson chloride salt or fluoride or bromide salt, we get a material with halogen surface termination, very uniform. Metal halogen bonds are easier to break. You can do after that surface functionalization with organic or other elements like chalcogens. You get the same terminations when you use, for example, chemical vapor deposition or when you use halogen etching of max phases. So again, by processing, we determine largely properties of these materials. What is also important, you remember I mentioned materials that made a difference in development of civilization were not the materials like diamonds produced in small amounts. Even diamonds nowadays can be produced much larger quantities and used widely technologically. Materials that can be made in large quantities. My former postdoc, he just started as a professor at University of North Texas, John Wang, is holding 1 kilogram of titanium carbide MXene here. My former undergrad student, she's a PhD student at the University of Chicago, Marley Downs, is holding about 8 liters of niobium carbide MXene delaminated into single to few layer flakes in water solution. Things here. We can make these materials by every single of this method scalably. We take ceramic powder basically, we etch it, or we use mix of gases here. So it's a scalable process. Moreover, a major breakthrough really happened in MXene synthesis just about a year ago or a little bit more. Dmitry Talapin's group from University of Chicago published this paper in Science in March 2023. It's a cover article reporting on CVD synthesis of MXene on the surface of titanium. But a group from Chinese Academy of Sciences and with one of my former students involved, published this paper in January this year on fluidized bed synthesis of MXene from titanium chlorides and methane. Now, titanium tetrachloride is an intermediate material for synthesis from ilmenite of titanium dioxide. If you look at white ceiling, white walls in the back, it's all titanium dioxide. You probably all use sunscreen with titanium dioxide. 3 million tons of titanium were produced in China just last year. About the same temperature, titanium tetrachloride is mixed with oxygen and heated at the same temperature. Natural gas methane is less expensive. Carbon nanotubes, 4,000 tons were produced in 2023, the ones that go into your cell phones, are produced at, again, even higher temperature than titanium chloride carbide MXene from methane when catalyst is injected. What does it practically mean? We have a process now. We can produce, if necessary, millions of tons of this material with potentially the cost between multi-wall carbon nanotubes and titanium oxide, titanium. It means that we can really make these materials a major game player in technology, from thermal insulation, and I will give you an example, to energy storage and many, many others here. Moreover, there is one more important factor when we talk about new materials, designing materials. There are materials which are wonderful. Gold is a great material. It's just not enough gold on the planet Earth. Thermoelectric materials. Potentially, we would be able to harvest a lot of energy if we would find thermoelectric without tellurium. Tellurium is as rare, approximately, as platinum. So it means that it's always limited to special applications. MXenes are made of titanium and vanadium, zirconium, niobium, moly, other elements next to it here. We etch away aluminum silicon if you use, for example, selective etching. Carbon, nitrogen connect titanium atoms. Oxygen, fluorine, chlorine, sulfur on the surface. So just in this group of materials, we can make a very large variety of materials here. So what it means that if we use abundant elements, and we have a highly scalable process from potentially inexpensive precursors, we can make these materials very inexpensive and very widely used here. Moreover, there is one more important factor: processing. I already mentioned that if we do selective etching to make MXene and get oxygen hydroxyl group on the surface, we etch the ceramic, making something called MXene clay, because rheologically it's really like clay. After etching, when lithium or sodium ions between the layers, they can slide with salvated ions like a clay. You can make a pot out of MXene or a coffee mug, but just like a clay, just like a graphene oxide, you can disperse it in pure water. No surfactant needed. And this is, again, big difference compared to graphene or dichalcogenides, where you need to use surfactant, you need to burn it, or metal nanowires, for example, for conductivity. And it's because there is a highly negative zeta potential as a result of this negatively charged MXene flake with oxygen OH on the surface. As a result, MXenes dissolve in solution, and they also come in different colors. Very important. It means optoelectronic properties are different, but also you can make things not only shades of gray, but you can make them really colorful here. And when you disperse it, depending on the flake size and concentration, you can make either very liquid 5 to 10 milligram per milliliter solution for engine printing on spraying walls with MXene, making shielding or thermal insulation, or you can make this 6 slurry, which is liquid crystalline. You can draw fibers. You can make films by Dr. Blading or screen printing from it here, and you don't need to burn the binder, just dry it. And you will see how easy it is. If my video plays, yes, it does. This is my student just spread the 6 solution of liquid crystalline MXene on the surface, let it dry, And now she separates this from a hydrophobic PVDF film. And you see, this is a 1 micron thin film, 1 micrometer. It actually has mechanical strength of good aluminum foil. And after drying, it is highly conducting. Imagine, for example, current collector of batteries. Instead of 10, 15 micron metal, copper, or aluminum, you can have micrometer thin film and shrink the battery this way here. But this is definitely not the best one can achieve. This is a paper actually from the work of Chunfeng Cheng from China and Ray Bachman, was published in Science. Chunfeng published a series of 3 very interesting papers in Science. They report by combining MXene with graphene and using basically this graphene oxide initially, water layers to align and stretch with much more rigid than graphene. MXene, it's not flimsy unlike graphene. Layers, making straight, well-aligned film and binding with organic molecules. They get mechanical strength of 1.8 gigapascal. This is twice the strength of steel. And this material is also simultaneously ionically conductive. They made a supercapacitor. So dream of structural energy storage when you have a car body or airplane body, being able to store energy can now be realized because of this assembled materials things here. So we can get materials which are very strong. And this again, big difference. We can make, for example, soft robots that can now really carry the load and eliminate motors, use electrochemical actuators in robotics. So this is when I talk about things that are revolutionary. I'm not talking about improving things, but doing something we have been dreaming as researchers, engineers for a long time and could not make because we did not have right materials. Now we are getting materials like that here. And of course, these materials can have many other interesting physical properties, quantum properties. Superconductivity has been demonstrated, chemically tunable. Magnetism, 2D magnetism is still to be shown. Ferromagnetism, antiferromagnetism have been predicted depending on the chemistry, things here. Some of the properties are still to be shown while they have been predicted here. But what is the most important? When we have this variety of materials, we can tune those properties. We can control them by selecting the metal, carbon, nitrogen, oxygen. We can change the surface termination, number of layers, arrangements of layers. You remember out of plane, in plane ordered structures. And we can also graft on the surface organic molecules. We can intercalate ions. So we can tune materials to get what we need for application, not take a single material that is given by nature, God, or your colleague at another university properties, but you can design them as you want. And there are many interesting things happening. For example, I mentioned MXenes have high density of state at the Fermi level. All bare carbides, nitrides will be metallic conductors. But the density of state is not as high as, say, in copper or gold. So by changing surface termination, you can change the density of state and even open the band gap. So we basically have metals which are tunable, properties of which can be modulated during the use like in semiconductors. Entire electronic industry is built on using semiconductors because we can modulate the properties. You can inject electrons into gold or aluminum, they don't care. MXenes do. For example, with less than 1 volt voltage, when we have protons between the layers, we can change between hydroxyl groups and oxygen on the surface. Hydroxyl gives us work function 2 electron, minus 2 electron volts, oxygen 6. And we can change thermal conductivity, we can check electronic conductivity, electromagnetic interference shielding in situ by applying less than 1 volt potential. And they come in a variety of colors. You might have seen this picture shown many times. This is a Roman cup from the 4th century, which is in British Museum. It is red in transmission and green in reflection because there are gold nanoparticles there with some silver. Last year, Nobel Prize in chemistry went to a group of scientists who discovered quantum dots. The first one, the old Russian scientist, originally he is working in the US now. His contribution was discovering plasmonic properties in different size metal particles in glass. This is exactly what Romans did without knowing, of course, the science behind. Now, look at titanium 2C. It's red in transmission, green in reflection. And we can actually tune properties electrochemically, making electrochromic materials many other ways. The main difference, there is no gold here. Titanium, carbon, oxygen, some of the most common elements on planet Earth here. And the reason is that there is a plasmon resonance peak at about 550 nanometer in titanium 2C MXene. But if we add an extra layer of carbon and titanium and make titanium 3C2 MXene, its peak shifts to about 780 nanometer. So it will become green in solution and kind of a purple metallic in reflection. And you can continue, of course, building with all the elements, any color you need here. So it's a great to have materials that can be produced from Earth-abundant elements in highly scalable way, in a variety, infinite number of compositions, process it from pure water if we need, without surfactant, binder, anything else. But is it good? Is it useful? If one can do the same thing with clay, graphene or graphene oxide, or chalcogenides, which also a large family, why bother studying MXenes? Few things I already mentioned to you. High metallic conductivity. For people who are not aware, after drying, I mentioned we get 20,000 Siemens per centimeter nowadays, more climbing towards 30. If you take graphene oxide and reduce it at 400 degrees C, you get 2,000 to 4,000 Siemens per centimeter. So it's an order of magnitude higher conductivity. And taking into account all the conductive inks and additive where people are trying to use graphene nowadays, it's a big application. But again, it can be processed like graphene oxide from water, but it's conducting like graphene, more conducting, and surface termination don't kill its conductivity. Come variety on colors, and actually stronger than any solution processed material. Ideal graphene sheet, defect-free, will be stronger and same here. But whenever you do graphene oxide, reducing graphene oxide, molybdenite, MXene will be stronger. Plus biocompatibility, modulation of properties, and many others. I am going to give you just a few examples. And what is wonderful here, actually, I have a clock here showing to me that I still have 45 minutes left. Doesn't matter for how long I keep talking, I guess, here. So what can we do with these properties of materials? There are many different applications, and you see it's all really started just like about 6-7 years ago. The growth is very fast. We started in our group from electrochemical energy storage, supercapacitor batteries. But many fields, sensors, just started to grow virtually like 4 years ago. And you see there are many, many different kinds of sensors. Again, the last year there is no like a deeper decline. It simply was incomplete here shown. There are many, many other applications. So people really started to explore how to use these materials. It's a very new book edited by 2 of my former students. Both are professors nowadays. And it provides a really like a summary of what the applications are for MXene, starting from discovery and synthesis to application. It's a latest, at least the book published just in July, about a month ago here. And there is, of course, the production of materials started in the world. Just in China alone, there are more than 20 companies selling MXenes and everywhere here. Let me, before I finish, give you a few examples of properties and applications. For example, I mentioned about thermal insulation, and I enjoyed listening for a while today a tutorial on measuring thermal properties of materials. I'm still a student here. I'm learning, trying to learn here. But what is important? Some MXene titanium-32 have very low emissivity. They're basically reflective as metals. They don't emit infrared radiation, so there is no heat losses through radiation. Some of them, like niobium carbide, have very high emissivity. They're good for example, space heaters, when you wanna electrical heaters to emit radiation and heat the environment. So they cover all the range from pretty much polished metal like gold to going above majority of other materials in emission. And we can tune select a material. What is interesting? This is about 200 nanometer logo printed in MXene and another one printed in carbon black and case. You see, this one on a 80° C heated hot plate remains cold. There is no emission light here. And this is a glass slide with MXene coatings, 3 different MXenes. You see they behave really differently, and you can see it from this plot, placed on a 120° hot plate. This film is 200 nanometers, and we get about 100 or 90° temperature drop on a 200 nanometer film. Because being metallic, these materials have thermal conductivity below 1 watt per meter Kelvin averaged in the field. As a result, they can outperform potentially any material. Instead of thick thermal insulation and then low emitting aluminum on the surface, we can make film which is 100 times thinner than a human hair, and it will be providing sufficient thermal insulation on the building. And you can spray it on walls, what you cannot do with thicker insulation. You can wash your t-shirt and infrared camera. It will be as soft with extremely thin film of material on the surface, but the infrared camera will show you drastic difference in the temperature. So you can keep yourself warm. You can have a silk dress, but it will be warm as a fur coat. So those are properties where you can outperform existing materials, including space fabric, including much thicker insulation. And those are first steps made really on MXene. Its thermal properties were just published here. In my group, we work a lot of energy storage, introducing nanomaterials for energy storage. And again, when we have materials which are conducting electronically and ionically conducting, what we can do with them? It's a big challenge, of course, for all the cars, time that you need to charge a battery, or even my computer. I spent some time on the beach today working with my computer, writing some disclosures that I needed to submit to our patent office. And the battery I ran down the battery. It takes me a long time. I need to bring the computer back to the room and leave it charging for a couple of hours. What does it mean, fast charging? It first of all means running a very high current through the battery. That's what fast charging, discharging. Battery materials have actually pretty low conductivity, including graphite anodes even. What happens when you run a high current through a poor conductor? Joule heating. So fundamentally, we're limited in charging batteries to a large extent by insufficient conductivity. And additive of a couple of % of carbon nanotubes cannot solve this problem here. MXenes conduct electrons, they conduct ions between the layers, and they have redox active metals, vanadium, moly, niobium, titanium, the same that are used in many current battery materials. So we can have redox energy storage. We're not limited by solid state diffusion because everything happens on the surface. And we have conductivity, which is higher by 2 orders of magnitude, at least compared to activated carbon using the fastest devices, supercapacitors here. And we showed that we can have redox energy storage. This is cyclic voltammogram. This peak show redox process at rates going up to 200 volts per second. So it means milliseconds charge and discharge in a protic electrolyte here. So we're not really limited in redox process rate. We're limited in delivering either ions or electrons. And if we do it, we can really have charge storage devices which will be just plugging in, plugging out, or exposing into any other way of charging and get them charged here. And moreover, we ran titanium carbide supercapacitor in acidic electrolyte like sulfuric acid in your lead acid battery for 500,000 cycles with only 8% of loss in performance. So it means it's probably at least 1 million cycle lifetime we can get here. Now we know how to inject ions, either intercalate like a lithium-ion battery between two-dimensional layers like in graphite, or get partial desolvation, get something we call pseudocapacitors, or get double layer capacitors, again by simply controlling the material, surface chemistry, and the electrolyte. And what is important, you remember I mentioned all the solutions that we can very easily print, engine print, 3D print, process by any other ways. We can again paint it on the walls. And as a result, we can make printable, flexible, wearable, even transparent energy storage devices. Batteries, supercapacitor, whatever you wish. So again, it moves us towards the era of Internet of Things, wearable electronics, which is again very, very important, particularly for, of course, all our personal electronics, but I think first of all for health care of the future here. And of course, you can go into many other fields, including energy harvesting. And let me give one example. I won't talk about solar or salinity gradient and others here. There is a technique which was developed probably 7-8 years ago, which is called transpiration-driven electrokinetic power generator. This is a fancy name for telling, take sea water, put it on the porous surface with some conductivity, let it evaporate, and as water evaporates and ions move, it creates current. And it has been shown on carbon, but the problem was that the current power was so low that it was purely like a curiosity, scientific, not useful. By using MXene, collaborating with Korean colleagues, we were able to push it by 2-3 orders of magnitude. This is a log-log scale, get into practical application. That's again talking about not improving something a bit, but making something that was considered but was impossible because of limitation materials. MXene are much higher conductors, better conductors, electrical losses. They are hydrophilic, and they allow much larger generation of energy. And we can talk about many applications. Oops, my flying pointer. Water desalination. There may be more water in Mexico, particularly from rain, at least in some part of Mexico, but many countries, Middle East, for example, fully depend on desalination. And again, whenever you have materials which are conducting, you can control transport of ions by applying potential. You can control it by controlling spacing between the layers, by controlling surface chemistry of material. This is an application. And this is not our work. This is analysis of literature published by someone already actually 2 years ago. But you can see, MXene were the latest comer into the game after MOFs, COFs, zeolites, transition metal, dichalcogenides, graphene oxide. They already got ahead in research of all other materials except of graphene oxide membrane being studied. And I'm sure that if they are not there, that's a matter of time they outperform themselves here. Another application, and I think I will give you 2 more before I finish so I don't get over an hour, microwave absorption here. Talking about Internet of Things, I'm holding this electronic pointer. There is my computer here, a couple of other devices. All of you have cell phones. All these devices interfere unless shielded and protected. And sometimes you want to put your cell phone in the pocket and it won't go on during my talk, or no one will be able to call you. You want to shield it. But moreover, break your cell phone. Any volunteers right now? You will see metal cages there, separating different components, different parts of it, again, shielding them from interference. Typically, metals are used. Those are the same 10-micron foils. It's actually thicker, probably about 50 to 100 microns in your cell phone for shielding. In 2016, we published a paper with Professor Chun-Min Koo showing that titanium carbide MXene aligns with copper and aluminum in ability to provide EMI shielding. 50 decibel, it means 99.999% of all signal shielded. 20 decibel, it's logarithmic scale, 99% signal shielded, enough for most everyday applications. But you remember I showed we can make freestanding 1-micron films, providing shielding for everything. And we can spray coat 50 nanometer film and provide 99% shielding of the signal, which is sufficient for majority of applications in everyday life or Internet of Things here. And this material, like titanium 3C2, it reflects electromagnetic waves. Titanium 3CN also does, but it actually at the same thickness outperforms copper, which is orders of magnitude more conducting. So there are different mechanisms of interaction with electromagnetic waves. And this paper, published 2016, within 5 years became the most cited ever paper in the entire field of electromagnetic interference shielding, because there are no breakthroughs. People have kept using metals or trying to replace them with carbon materials which did not provide sufficient performance. But you take another MXene, vanadium carbides, and they will be absorbing electromagnetic radiation. You can disperse them in metal and get very good absorbers here. So this is how you can tune. And we can incorporate them into textiles. We can make fibers, we can make textiles, and they can be used for thermal insulation. They can be used for shielding. We can print, or we can on textile or actually knit directly from MXene fibers, antennas or other devices. And this is again goes towards wearable electronics, printable electronics, epidermal electronics things here. Sorry, jumping far ahead here. And another example, which actually was inspired by my colleagues from Canada, again from the area. I'm not an expert at all, but working with a colleague from University of British Columbia, Mohammed Zarifi, who used MXene materials for printing, they mentioned to me that there is a potential problem. Waveguides for satellites that people, or future space mission, people try to print them out of metal to be able, for example, to create them in space on Moon or Mars or International Space Station. And they are heavy. And you understand cost of payload going to space. And traditionally, it's basically a metal tube which guides signal to from antennas. So what they suggested to do? They asked whether we can coat them with MXene to make them conducting like metal but lighter. They printed from nylon the same structure, which is 10 times lighter compared to the metal waveguide. We deep coated, simply dipped it into MXene solution and got a waveguide that performs pretty much just like a metallic one. And they have very complex shapes. Some of them, they can be designed. If you go online now, open Google and look for waveguides for satellites, you get prices from $500 to many thousands. And of course, there are extraordinary prices for the one special design and very heavy. But amount of material we used is in milligrams. So we can make this piece of equipment 10 times lighter than the currently used one. Easy to manufacture. There is no machining of complex channels internally that can be twisted or others here. And actually cheaper, even at the current cost of MXene, which is high.
So this shows how understanding property of material, one can develop technologies, useful application, and many others here. This work, again, collaboration with Korean colleagues, we replace electron transport layer in OLEDs, organic light emitting diodes, and you can do very similar work, and we have been doing on solar cells, replacing ITO, indium tin oxide, with titanium carbide MXene, 10 nanometer transparent film. ITO cracks where you bend, so their goal was to make devices which are flexible, bendable, foldable. But because we can tune the work function in MXene, this logarithmic scale, luminance, brightness, also increase by order of magnitude. So they not only make it flexible, they make it also 10 times brighter. And now we are working on a paper also showing that you can make stretchable devices in addition here. So you can have a display, you can have OLEDs that you can wear, which will bend, flex, and won't be damaged, and will be much, much brighter, consume much less energy here. There are many other applications. Biomedical research, because of biocompatibility of MXene, is expanding quickly. From photothermal therapy, the same plasmonic peak I showed you like in a gold, niobium carbide, titanium 3C2 absorbing near infrared or infrared, one can destroy cancer tumors by using infrared laser and delivering MXenes to tumors here. One can use it for electrical engineering, maybe for conductive tissue scaffold for the heart tissue replacement. Many other applications, as this example, this picture is borrowed from my collaborator from Penn, Flavio Vitale. And again, the range is greatly increasing. And I already talked to one of the Mexican students earlier today working on biosensor with MXenes. So the work is ongoing here. Let me give you just one example, work we are doing with colleague from Penn, Flavio Vitale. Things here. Wearable sensing. So I'm pretty confident 10 years down the road, none of us will be going to a family doctor for a regular health check or a doctor for majority of disease diagnostics here. We will have a sensors which will send a signal probably through your cell phone or other devices will have at that time to a supercomputer which will diagnose the disease. And those sensors that we can wear, sportsmen, astronauts are already using them very widely nowadays here. Typically, gold or platinum is used. Gold, platinum, more conducting than MXene. But MXene, because of hydrophilic surface, has a better impedance with skin, so contact resistance is lower. As a result, you see intensity of signal, this spike intensity, higher compared to gold sensors of the same shape or commercial gold sensors here. So again, we're not competing with graphene or other materials. We are competing with gold again and are outperforming gold in these applications here. And same is true for implantable neurosensors and many, many others. Maxitronics, people have, Hussam Al-Sharif from KAUST, from Saudi Arabia, introduced the term Maxitronics for the future generation of electronics based of MXenes here. There are many, many more applications, and I don't want to bore you and give you some time before the reception left here. So, message I would like to leave you with here. We have this wonderful and very large and very quickly expanding family of materials that can be built of common abundant element, many of them, in highly scalable processes with a variety of surface chemistry, composition, structures, number of layers, optoelectronic, chemical, electrochemical, other properties here. But we're still in the beginning of the road. Consider how many people work on graphene, a single materials made of single element carbon, not counting oxygen or H maybe or a few other dopants, eventually things here. MXenes have probably received about 0.1% of funding and effort that graphene alone received, and there are infinite number of materials in the system. You can imagine how much work here to do, but what it means that everyone here can discover new materials. You can go back to the lab and start making materials which no one studied before. We need to understand properties at very fundamental level of these materials, learning how to control them much better than we do today. And of course, develop application, whether you work on sensors, tissue engineering, build a better battery, or dreaming of a space flight, and making a spacesuit which will be as comfortable as t-shirt and jeans many of you are wearing today, but will enable a spacewalk. These are type of materials very often in combination with other materials, with graphene, dichalcogenides, nanotubes, including actually clay as well can be used here. We don't know which of these many applications. I gave you a few examples, but they're already today economically viable, when they can improve by an order or two of magnitude performance or enable things that could not be made before. But we still don't know where the major application will be. I personally tell you, in my opinion, this is not a single major application. It's not a single hit. They will really affect many, many areas of technology, because we will move one way or another to this assembly of low-dimensional materials, building from the atomically small blocks our future materials. Actually, Graphene and MXene already have a journal, Graphene and 2D Material, published by Springer, the journal, the Graphene Council and MXene Association. And I have a whole bunch of flyers, and I made them available, finishing, thanks for the sign from the chairman. Couple just advertisement before I wrap up here. We just had a third International MXene Conference in Drexel. There was the first Euro-MXene Congress in June in Spain, Valencia. There will be sessions at UCAMAT Conference, Gartenovi, European MRS meeting, Warsaw, MXene Symposium, and the 5th International Conference on MXene in Xi'an, China. My Chinese colleague told me they're expecting about 2,000 people there. Remember, I showed you a slide how much work there. I will be chairing a Nanomaterials for Application Energy Technology Gordon Research Conference in Ventura at the end of February, and I encourage everyone to submit abstracts to this conference, many opportunities to meet the MXene community. And this is my very last slide. Science is beautiful. Not only MXene, but our other nanomaterials are beautiful, but they're difficult to see, they are small. We have to use microscopes specifically to visualize them, or computers, or others. And for 8 years, together with our former students, my former postdoc, research assistant professor in my group, Babak Anasuri, who is now a professor at Purdue University, we have been running nanoartography competition. This is online science as art competition. We give prizes, $10,000 in prizes, up to $1,000 prizes. Some of these pictures appeared on covers of books and magazines. One of them was a cover image for the World Science Festival in New York a few years ago. 3 million people, according to organizers, saw it here. So if you create images, optical, IFM, SEM, TM, doesn't matter. Use your artistic talent or artistic talent of your friends and create small pieces of art, and you can become rich and famous if you submit them to nanoartography competition. And the deadline, as you see, is at the end of September. So again, you can start working right after the conference on this. And this is my last slide. I still have 45 minutes left here, Felicia, according to this clock here. But I'm going to stop now, and if questions are allowed, I will be glad to take some questions. Thank you very much.
Thank you. Thank you very much, Yuri, for the impressive talk and also the great overview, really going from the materials production to the application and finally actually understanding you can become rich with art rather than MXene. I was expecting the final thing was MXene. Any questions from the audience? Questions? There's one down there. Yep.
No.
Do we have a microphone for? Yep. Thanks.
Greetings. I would like to ask the question if, well, what could be the applications of MXene into mechanical design for product manufacturing in a large scale? How can we as engineers understand or have a better understanding of the material properties in order to consider that for product design in a large scale, just as you mentioned regarding, for example, the medical devices from the future?
That's a very good question here, because whenever we have a new material, you cannot just go to a handbook and get properties of this material in design. And this is actually very often an obstacle to introduction of new materials, because say mechanical engineers, they know their tables of materials, they know how to design, they know what properties to plug in. You cannot plug in conductivity just of titanium carbide film and correctly calculate electromagnetic interference shielding. The software will tell you take aluminum instead. So we need to work together with the design community. And it seems to be really something that any high school kid can do. 3D print from a polymer, a waveguide, dip it into a solution just like we dipped the t-shirt I showed you before, dry it, and make a piece of equipment for space flight. But this is not what a mechanical engineer in Boeing would do. They would go to a company that makes waveguides and ask them, deliver to us please a waveguide. And those will get them an aluminum or copper waveguide, which will be much heavier things here. I think this is where we need to build bridges and dialogues. We as material scientists need to talk to materials design community, to mechanical engineers, product designers, and tell, look, we have new materials. We can now make them from solution. We make a coating, metallization without vacuum and evaporation of metal. We can do it by spray coating or deep coating on the surface, or printing, or other techniques. And this will take time. And without us going and building those bridges with manufacturing community, it will take even longer. So I think this is a very important topic you raised.
Thank you.
Thank you. Any other questions? There's one down. Oh, yeah.
Sir, thank you for your talk. Extremely interesting. You mentioned in your talk that MXenes might have antiviral, antibacterial properties. And honestly, I don't see any mechanism. Why is that? It seems to me totally, I don't understand how this happened. Can you explain? Because you mentioned that might be for antiviral.
Okay, look. First of all, this is a work I'm referring to. It's not my work. It's a work by several other groups like Acela, Yılmaz in Turkey here. They have highly charged surfaces with zeta potential in solution like minus 50 millivolt, and also reactive surfaces potentially here. So when cells come to the surface, surprisingly, they're biocompatible, but some of these MXenes have shown to be killing the viruses. And this study was actually done for the first time, started during COVID, when everyone was looking for antiviral properties things here. I cannot explain the mechanism, and I'm not sure the bioscientists who reported and do. But there are several reports from independent groups reporting on this. Is this the most important application for MXene? I'm not quite sure, but it is something that has been reported in the literature, and this slide I showed is summarizing where people are exploring MXenes nowadays.
Okay, any one here?
I see one question right
No,
here
there's
in the
one
second
here,
row.
one here already. Yeah, there's one here.
Oh, yeah.
Yeah.
One in the back.
Waiting for the microphone, yeah.
Thank you. Very, very interesting talk. Thinking that they are like a layer material similar to graphene, as you mentioned, do they have also tribological properties of interest because it's a surface engineering method?
Yes. I did not talk about it because it's impossible to cover everything here. I think Aniruddha Sumant is supposed to be here at this conference. I don't know. I think his talk somewhere in the program. His group, from Chile, another group from Austria, actually collaborate with Babak Nasuri, whose name already mentioned here, showed they don't come to super lubricity, but they come to pretty low, like a 0.02 friction coefficient, and also very good, very resistant, especially under heavy load. And then explained by formation of tribofilm, because carbides and nitrides are very hard material. But being in 2D flakes, they don't wear the other surface. They pretty much prevent the contact between the surfaces, forming this tribal layer and protecting it here. Yes, so tribological applications are the ones being explored. And the first paper appeared, I believe, something like just 3 or 4 years ago. And with a number of groups, Andreas Rosenkrantz from Chile, Aniruddha Sumant, many others working on applications. I could not cover everything. I just gave a snapshot, and it was probably already too much, and I was probably too superficial.
One over there.
But it's a huge family of materials.
Thank you for your nice conference. I would like first to make a comment. I remember I saw your first conference in this meeting about 25 years ago in a symposium that just lasted 1 or 2 times. It was a conference on that was devoted to future researchers that had brilliant futures. And I think with your talk, you shows that. For that, I really congratulate you on your work. And my question is regarding your materials is this. How stable are these materials to temperature or to ambient changing conditions?
This is also a very good question. First, yes, really, in 5 years, the progress has been enormous, and you can see that this plot from publications, how they really grew. Stability is an important question. And actually, carbides, nitrides can hydrolyze on oxidize potentially. But it all depends on the material. We just published earlier this year a paper. We reevaluated old samples which we just kept in the lab. And we have a sample of a MXene paper airplane, which we published in PNAS in 2014. And it is still conducting, and it can still fly. We know that under ambient conditions, 10 years at least, but this was material which we know in solution when you take single flakes, about 100 times less stable compared to titanium-332 we make now. But it also depends on composition. Thicker MXene, niobium-4C3, will be much more stable than niobium-2C. So thinner layer, oxidize, hydrolyze faster. When they are pure water, exposed to temperature, they will oxidize. But dried films have been just shown in another PNAS paper by Babak Nasuri and collaborators from University of Pennsylvania, is stable single layer flakes in the air at 600 degrees C. So I would say they are sufficiently stable for a large variety of applications, but they don't have infinite stability. And of course, like other low-dimensional materials, even in protective environment, like vacuum or argon, they will start above certain temperature, typically between 600 and 1100 degrees C, transforming to two-dimensional to nanocrystal, three-dimensional, to minimize their free surface energy, because they will start losing their surface termination. So this is important, one of many issues I did not cover today, But whenever you work with these materials, you need to look into stability. But you saw Marley holding a container with 7 or 8 liters of solution of MXene. We don't make them in glove boxes. We process them in water or emulsion salt and wash them in environment. But we suggest to keep solutions refrigerated, just like perishable food, before you process them. When you process them, typically, at least under ambient and other conditions, you don't have problem for majority of materials.
Okay.
Yeah, actually.
There's one over there, yeah.
Thank you, Dr. Yuri. Very nice presentation. I am not from MXene, never grown myself, but I learned something new. But you have shown your different perspectives, applications from fibers to biosensors, good CV response, and everything. It's good, actually. It's great, actually, in fact. My question is, for example, every material, they have some constraints or limitations. So if you have to overcome something in MXene, for example, if you have to look for something new, what could be the biggest challenge for you right now in MXene? What you want to overcome means in future?
Look, first, let me disappoint you. No material is perfect, not even MXenes. So every material has limitation. And this is why I started my presentation talking about variety of 2D materials or nanomaterials in general we can build as building blocks of future technologies. Yes, it's predicted possible to make semiconducting MXenes, but we have so many good two-dimensional semiconductors. Does it make sense? To me, it doesn't look attractive. You probably won't be able to make a dielectric MXene, just simply because too many electrons in these transition metals and carbon nitrogen, there are things here. So there are limitations of things you cannot make. Now, for practical applications, I'm at the moment extremely excited about thermal properties, because maybe this is the latest thing we started to work. We found it extremely attractive, and we know we are very far from the maximum what can be achieved there, and it's already amazing. So I think interaction of MXenes, controlling interaction with any kind of electromagnetic radiations, from gamma rays to radio waves, and everything in between. I think there are enormous opportunities, because we can truly tune materials for the wavelengths, terahertz, optical, visible, UV, infrared, microwaves, all is there. And I think this is where probably the first big application will come. But sensors, conductive inks of any kind for whatever application you can imagine, and where people use metals or graphene or nanotubes today. So I think it's a huge range. And again, referring to what I mentioned at the beginning, I don't know everything. Even my large research group doesn't know everything, cannot do everything. That's why I'm talking to a broad audience like here, because I want you to basically look at MXene through the prism of your knowledge, your understanding, your experience, your area of interest, to think, okay, materials with these properties, these morphologies that can process this way, how can I use them in whatever I do? And you may find a new application I would never imagine even exists, because I don't know that there is a need for such a thing. I would never guess about use of MXene in waveguides, for example, or many applications we have been exploring, like, for example, implantable brain electrodes. I would think people were perfectly fine with gold.
One more here.
Great talk.
Well, great to see you again.
Question. We are working intensively on growing these crystalline diamond films or polycrystalline to cool down. How would the thermal transport of this MXene compare with diamond, which is the highest we know up till now?
It's low. That's why we can do thermal shielding.
Okay.
We don't fully understand why. It may be very useful for heat shielding, infrared styles, warm clothes, or thermal insulation in general here. But there are materials like, for example, not graphene, really, it's a graphite, 3000 degrees C, that people use as heat spreader in cell phones, competing with your CVD diamond, nano diamond here. So I think this is exactly where we need complementing materials. Sometimes you need to spread the heat and remove heat from a chip, computer chip. Sometimes you want to insulate the same computer chip somewhere in space where it's cold outside and you want to keep the temperature. So my opinion, they will be very complementing because they will cover different part of the thermal management equation we're trying to solve.
Okay, great, thank you.
Any other questions? Any other question? I have one question myself actually related to the growth, CVD growth that you mentioned. So what's the grain size you can grow these MXenes at the moment?
CVD at the moment small. It's limited at the largest flake we saw maybe a couple of microns. But as I mentioned, this was just discovered virtually material. So no one knows how to make wafer scale MXene. Now, it looks to be a routine for graphene right now. Go back 15 years down the road. How much money was put in transforming silicon carbide wafers to have a graphene of electronic quantity? How much people play with nickel, copper, and I don't know, probably just in CVD growth of graphene alone, more money was put than in all these explorations of MXene together around the world here. So lots of things need to be done, but I think this is an opportunity, not just a challenge, because it just takes someone who has experience in wafer scale growth, in chemical vapor deposition. And there may be other methods. You can make maybe ALD layer and crystallize it, or do MOCVD or something else. It requires, again, expert in those fields, understanding, okay, this is a problem that exists and I have an experience. I can take on it and solve it eventually.
The limitation for graphene was actually the fact that you needed a catalyst, right?
Yeah.
So do you have the same for MXenes?
No, but you need to make it self-limiting, because potentially carbidonitrides, they can grow, but they can grow thick. People, for example, developed methods of growing nice, they call them 2D crystals, but in fact they are from nanometer to several nanometer in thickness. So it's not the same single layer with all the atoms, you know. I show you like an niobium 43, and all billions of flakes there will have exactly the same thickness. And in this case, every crystal will be slightly different. So I think finding this self-limiting mechanism, it happens in the gas phase. No one just demonstrated on the surface, but there is no reason what cannot be done.
That's a good message for students here. You know,
yes,
if you want to work on this, that could be.
Exactly. This is basically an opportunity for everyone. Exploring new materials in new application, this is something what you can do when you're young. You know, like select a topic which is novel, which is potentially exciting, and if you like it, and if you feel that you can contribute, and everyone can contribute, doesn't matter whether your background is in physics, chemistry, chemical engineering, mechanical engineering, electrical, biomedical, medicine, material science, and so on. There are opportunities. They're just different, and look for something exciting. And again, let me refer you to one of my first slides. Also things that can make a difference. That, you know, if you spend years of your time, whether it's your PhD research and maybe the entire career, at the end, you know, you did not waste this time. You worked on something what was important, whether you solved the problem or not. And again, thank you very much to the organizers and to everyone here in the audience.
Before closing, actually.
Thank you very much for your talk. This is a craft that, you know, is made here in the region, and it's, you know, it is explained here how they make it.
Wonderful.
Very
yeah. Yeah. Again, thank you very much to the Mexican Materials Society for this here. Yeah. Wonderful. See you at the reception.